So we've discussed the basic trade-offs that are present in statistical estimations. The desire is to have a high confidence level, a low margin of error, and a small sample size. The problem is these three objectives conflict. So for a given sample size, a high confidence level will tend to generate a large margin of error. For a given confidence level, a small sample size will result in an increased margin of error. Reducing the margin of error requires either reducing the confidence level or increasing the sample size, or both. A common question from business decision makers who are planning an estimation application is, how large a sample size do we really need? So in this example, we've run the equation backwards and rearranged it using algebra, so we've solved for n here. So reduced it to the quantity of z sigma divided by e, or margin of error, and then square that result, or you could square each individual value. So in this example, the population mean should not exceed 30, with a population standard deviation of 200 at the 95% confidence level. So the 95% confidence level gives us a z-score of 1.96, and then plugging the other two values in and squaring the result results in a sample size of 171, or 171 data points. Now, that equation assumes you know the population standard deviation. This may be the case in some situations. Most likely we won't know the population standard deviation. So to get around this problem, we have three approaches. One is to use a value for sigma that is considered to be at least as large as the true sigma. This is to provide a conservatively large sample size. The second option is to select a pilot sample, or a sample from a population that is used explicitly to estimate sigma. And the third option is to use a range of the population to estimate the population standard deviation. So recall from the empirical rule in Chapter 3 and in Chapter 6 of the normal distribution, both sources suggest that mu plus or minus 3 sigma contains virtually all the data values for a normal distribution. If this were the case, the mu minus 3 sigma would be approximately the smallest number, and mu plus 3 sigma would be the largest value. So remember that the range equals maximum value minus the minimum value, so the range is approximately equal to 6 sigma. We can therefore obtain an estimate of the standard deviation as the range divided by 6. So let's try this out in Excel. Open Excel file Paychex and answer the following questions. So one way we can determine the margin of error at the 98% confidence level is to use our data analysis package. And we saw earlier that we can use descriptive statistics to achieve some of these things. So we'll set our input range and select the output range. We want summary statistics, but we also want confidence level for the mean at 98%. And you can see this is our margin of error, 1.195, and here's our mean. So we would say our confidence interval at the 98% confidence level would be our mean of 36.161 plus or minus 1.195. So now the second part, we want to determine the sample size required to produce a margin of error, or E, equal to 1.4 with a confidence level of 98%. So we'll assume the population standard deviation equals 6.22. So we know that E, or the margin of error, is 1.4. We have a 98% confidence interval, and they told us that sigma is 6.22. To determine the z critical, I'm going to use the norm.s.inv, again 1 minus the confidence level, divided by 2. And once you have that, we can then compute the required sample size. And since we always want to round up when we have a partial value, I will use a roundup function and set it to 0 digits. So we can see 107 is our sample size required. So the average for state and local workers is less than that of the federal government workers.